Did you all get my announcement? Okay, cool. Sorry I'm late. 10 plus. We had a little bit of confusion. Workshops on, workshops off, workshops on. And then I miscalculated my day. But so we'll go to say 22:07. Obviously, if you have to leave early, that's cool. Otherwise, how's our preparation going? We're good? No? Bad? Medium? The important thing is to remain positive, regardless of whether our preparation is going well or badly. All right, so just about ready to start. I guess the recording's on, so if there's anyone watching the recording, we probably won't get the last 10 minutes of whatever we do here. So if anyone watches at home or you watch at home and you forget what we did in the last 10 minutes, just email me. Do we have any specific questions we want to talk about? Anyone come with anything?
Sure, there are some good questions on the exercise.
Sure. So so just in general, I'm going to suggest that we do stuff from, say, tutorial 8, tutorial 9, exercise sheets, all of that. But did anyone have anything they were stuck on or a particular idea that you want on the agenda? Otherwise, I'm going to suggest that we focus on the stuff at the end that we've done recently, because I think tomorrow you're getting like a broad overview where you can just pull out stuff from everywhere. I don't mind taking questions from anything in the course, but my guess is going to be that the rustiest stuff is the stuff that we just didn't have enough time to practice yet. Okay, so maybe we should look at tutorial 9, because maybe that's what we had the least time to practice. Sound good?
Which one is it? It's the last one.
Yeah, tutorial 9 is the last one. It's the one where we were looking at...
Yes, especially we can please do 2A.
2A.
I remember the question.
2A was, well, so 2 was this list of all these different series, and the hint was, there was like an A, B, C, all the way up to H. They give you a bunch of different series, and they said, are they convergent or not? You justify your answers. And sort of the hint here was that because we recently learned the root and ratio test, probably this is testing the root and ratio test mainly, but it's still also perhaps asking you to consider other stuff that we've done before. So is that the one you're thinking of?
That's what 2A is.
Yeah, okay, cool. And any other questions from tutorial 9 particularly?
2H.
2H.
Number 1, please.
And number 1. So maybe we should do like sort of all of question 1. Because question 1 is kind of like, it's just like a check and reasoning kind of question, but it actually says something quite deep that we might want to remember. And I'm not sure that that's fully emphasized in the question. It sort of just asks you to check these different results. But we might want to kind of summarize what we're learning from question 1 as well. But okay, so I'll write that down. So let's say we want to do TUT 9, question 1, and question 2A and H. Okay. Anything else we see that, do we just want to do the whole TUT maybe? But we probably don't have time to do the whole TUT. So, as you've seen from the previous test, it's not the worst idea for us to talk through some of these comprehension proof things, because you did get a comprehension proof question in the last test, and you probably will in this one, or at least probably will in the exam. Now, you may want to play the game of guessing which comprehension proof type question they'll give you. I don't know. I don't have a good feel for that, just because this is the first time this course is being given. So I'd say everything's fair game. So if you have any specific questions about question 3, we can talk about it. If we run out of time, there's Murray tomorrow, and you can email me. But yeah, if we have time, we'll do question 3 as well, I think. I don't think that's a waste of time. Yeah.
Would they ever ask us to prove a theorem that we proved in class?
No, not from memory. As far as I understand, that's, again, always double check with the lecturer, but my understanding is actually for pretty much every math course in this mathematics department, and pretty standard around the world, the idea is if we prove something for you in class, the point of us doing it in class is that it's like reasonably hard and reasonably lengthy or reasonably deep in new result, that we don't necessarily want you to just like memorize the way to do it. So we still want you to know about it though. So how do we test that? It's like, okay, give you some shorter questions that require you to use those results, or give you the whole thing, but like guide you through it. So that's what you're seeing with these comprehension style questions, is like, we don't want you to memorize the whole proof, we want you to understand how the proofs work. Because otherwise you get in the situation of just like memorizing this list of theorems, just like boring and also doesn't like convey understanding. So we want to make sure you actually understand what's going on. Like, why does this theorem work? Why did certain arguments within the proof work? Because then we keep reusing those arguments as well. Yeah. Okay.
Yeah, can you also like go over strategies and reasonings when given a series, right? To determine whether it's convergent or not? Like what test should we use?
Okay.
Like that, like
Sure. Okay. So let's write that here. So sort of strategies for checking if a series converges. Okay, that's my notes for me, so don't worry if you can't read what the heck I wrote there. Any other stuff that we want to kind of, it's probably enough to fill up a whole hour and a half, but certainly if you have something else, maybe I can email you the answer to it, or we can put it together. Any other specific questions? Anything in the back?
I do, but I will give you.
No, you can tell us.
Say sometime later. I need to set up my little podcast.
Oh, okay, sure, no problem. So just stick up your hand at any point if you want to add anything to the agenda, if you just have any other questions. So strategies for checking if a series converges, that's probably like a natural place to start. Because, you know, maybe what I suggest we do is we do this, okay? We just discuss this as quickly as we can, because honestly I could talk to you for like 3 hours about that, but we'll try to do like a very quick overview of this. Then we'll do some examples, which are here, and then we'll try to get through question 1, and then maybe we can add some stuff on the end if we go reasonably well through that. So the strategies for checking if a series converges, there is a previous recording on this as well, so I don't remember exactly what week it is. It was not last week, it was not the week before, I don't think. I think it might have been like 3 weeks ago or 4 weeks ago. So there is are you aware of that? Because there is a recording there where we kind of like, we hadn't filled in everything, but we kind of broadly said, well, there are different types of questions you can get. So I'll say that again quickly, but again, we could spend 2 hours doing that alone.
I'll go over.
Yeah, yeah.
Roulette tab.
Yeah, there should be all the old recordings are there on the Roulette tab. And so there's, I think, sort of at the end of one of the weeks, we round about tutorial 6 or right before that, at the end of the lecture, or at the end of this workshop, we did a little kind of overview, and then the next week we started the workshop with an overview. I don't know that the next week got recorded. I hope it did, but but anyway, let's quickly do it. So the idea is like basically you get two types of questions, broadly, roughly. And this is for series converging. So I'm not going to write down everything, just so that we can go in some reasonable amount of speed, but hopefully this gives you the idea. So there's two types of questions, roughly. So type 1 is like calculate the sum or argue divergence, okay? So this is like you need to produce a number. Like you need to sum up this infinite series and produce a number, okay? And as soon as you see that, you just rule out, like, you just forget about a whole lot of other stuff, because you don't want to be juggling 15 different ideas in your head that you all had to memorize. You just want to say, oh, I've got to calculate a sum. Well, does the comparison test calculate a sum for me? No. Does the alternating series test calculate a sum for me? No.
By calculate the sum, are we trying to find the number that the series
Exactly.
converges to?
So when I say so when I say this, what I mean is find some like x, which equals the sum up to infinity of some an. Okay, find x. Okay, so literally find that number. And does the comparison test do this for you? No. Does the alternating series test do this for you? No. Does the ratio test do this for you? No. So we learned all these different tests. None of those tests tell you what that number is. They tell you whether that number exists or it does not exist. Okay. Now you might say to me, well, argue that it diverges. Maybe I would use those tests to argue that it diverges. Okay, fair enough. So that's going to require a little bit of like kind of subtlety on your part. Like if you look at a series and they say find the sum or say if it diverges, and you can look at it and you say like, this type of series is going to be easy to check if it diverges with the ratio test. That'll take me 1 second. Let me check. Oh, look, it diverges, or something like that. Or you look at it and you go, okay, I can compare that by p-series to something that diverges. It diverges, okay? So I don't want to say completely forget about all the tests we learned, but in general, if they tell you to find this x, all those convergence tests just don't find that number for you, right? If they do, then you've proved something magical and you should share it with us, right? So that's the idea, is you want to have categories of results in your head. You say, this is this type of question, so these are my tools that match that type of question. This is this type of question, these are my tools that match with that. So, okay, so what's the second type of question? We'll review what the tools are, but first, let's just say, what's the second type of question? Does some infinite series converge or diverge? And then they can ask you further things like absolutely or conditionally. Okay. Okay. So those are sort of two different types of questions. Okay. So what are your tools for one? Okay. So you have a list of tools to apply in part one. So to check diverges, okay, well, there's a lot of stuff to check if diverges, so I'm not going to list them all, but usually I would say use something quick. Okay. But then again, this is going to be up to your own strategy. So what do I mean by use something quick? I would say, limit an as n goes to infinity, when an is really that sequence that we're adding up, is not equal to 0, implies diverges. That's often quick to check. Okay? So this is an example of how you could quickly check whether it diverges. We've covered that a lot, right? So you take the limit of just the sequence that you're adding up. If it doesn't go to 0, this series diverges. So maybe I could even make that really clear. implies an sum to infinity diverges. Okay. What other things? Others. Geometric series. Ratio test. Ratio test. Etc. Okay. If you look at something and it looks like a geometric series, you can often say whether it diverges immediately. I would say maybe compare with P series, etc. Okay. So these are all tools, just checking quickly if something diverges. Okay. And we really want to feel like we can do that within 1 minute, you know? If it takes longer than 1 minute, then maybe we're using the wrong tool, okay? Under part 2 here, we're going to talk about how do you know which test to use for a given type of series. So we'll get to that, don't worry. And I'm just saying, these are generally quite quick to apply, yeah?
Yeah, so you're saying for checking divergence, the test shouldn't take like more than a minute?
Hopefully, yeah. If we apply the correct test, I'm talking especially in these question 1 type problems. Okay, so in question 1, you saw this in one of the tutorials. I think it was tutorial, might have been 7, but maybe it was tutorial 6 or tutorial 5. It's like question 1, you know, check if a series diverges or converges. If it converges, calculate its sum. If it diverges, say why. So in that situation, when we're actually being expected to calculate a sum, they're not going to give you a series that's impossible to calculate the sum of. Do you know what I'm saying? And so sort of in those cases, these are very fast checks for the types of series that we know how to sum up. Okay? That's sort of roughly what I'm saying. Okay? But you're going to have to fill in a lot of blanks. This isn't going to be a comprehensive sort of guide. You're going to have to go back and watch the thing, fill in the blanks, but this is the idea. There are certain checks for something, if something diverges, that are very quick. If I write down this, the sum of 1 over 2 to the n, you can tell me whether that diverges or converges within 10 seconds, okay? You see that n, geometric series. Is the thing greater than 1 or less than 1 or equal to 1? Less than 1, done. Converges, okay? If I give you this, diverges, done. Okay, so we want to get into the idea that if we're asked to calculate the sum or argue that it diverges, we want to know quickly whether it diverges or not. Because if it converges, we need to focus our time and our effort on calculating that sum and using tools to calculate that sum. And we don't want to be going down that road for long if it turns out the thing diverges, right? So I don't want to be, okay, this one's probably a bad example. But let's say they gave you something like, I think they gave you something like this recently, n over log, natural logarithm of n, okay? And they're like, calculate the sum or show diverges, you know? Now, are you gonna go down the road of trying to work out what the partial sums are, checking if it's okay, it's not a geometric series, so is it telescoping? No, we don't want to go down that road. We don't want to spend any time. Just want to do a quick sanity check. Is it possible that it diverges? You look at it and you're like, well, this, the limit of this over this, by this rule, is not equal to 0, so it diverges. So we don't spend any time trying to work out what the sum is. Do you know what I'm saying? So we want to be in the rhythm of knowing which of these sort of quick tools we can pick to guess whether something diverges or converges. And if it converges, then I'll show you the tools to actually calculate the sum. Yeah.
Just for that specific one, the limit of a over the limit of n is in goes infinity.
Sorry?
The limit is n goes to infinity. N over n of n is equal to infinity.
Yes.
Awesome.
Yes, correct, yeah. There's a few ways to argue this. You can use comparison tests, you can take L'Hopital's rule. But the rough idea even that I would say, so you know those rigorous ways of checking, but as you do more of these problems, you want to feel like you actually know this is a polynomial in n, this is a logarithm in n. Polynomials in n grow much faster than logarithms in n. So actually even faster than that. But if you're not sure, just L'Hopital's. This is a great one for L'Hopital, or you could do comparison tests, but now we're spending a little bit too much time on it, right? But anyway, that's the sort of thinking I want to say. So if they ask you to calculate the sum, you need to produce a number, and there's going to be a short list of tools to do that. However, before we go down that road, just glance at it and say, can I just quickly check whether it diverges? Is there one of these 3 really quick things, maybe 4 really quick things to check if it diverges? Spend 30 seconds on it, and maybe you save yourself 10 minutes, you know? Okay, so we've checked if it diverges, and suppose we think it doesn't. But we're asked to calculate the sum. So how do we calculate sums? What tools do we have to do that? Okay. Well, calculating. So when I say calculating, I'm really meaning producing a number, producing an answer. Calculating sums. Okay. Geometric series. You know the result of a geometric series. Okay. So you check, is it a geometric series? If it's a geometric series, you can find out what the sum is very quickly. You can check telescoping. We've seen that. We've seen a few examples there of telescoping. Okay, that's been in a few tutorial questions, so I would say that that's fair game. That they can say, check out this thing. Does it look like it's telescoping?
Is telescoping an alternative?
Sorry?
Is telescoping an alternative?
It's the one where you have something that looks like, it's not just alternating, so alternating, but I think you know what I mean, right? So an alternating series is just that the terms alternate positive, negative, positive, negative, positive, negative. Telescoping means that the terms actually cancel. So you have something like A0 plus A1 minus A1 plus A2 minus A2, something like that, and you could group it so that all the middle terms cancel, and you just get left with this minus an as the last term. That was telescoping. We had a few examples like that in, struggling to remember which tutorial it was, if it was either 5, 6, or 7. It was one of those, but it was question 1. They had like, I think, 2 different questions that were telescoping. So you check, could it be telescoping? Not many things are telescoping, but the key to looking at that was, you know, if you see something like this, okay, when you see n plus 1 and n both appearing in the formula somewhere, you might have a hint this might be telescoping. Okay.
What is the hint when you see them both appearing in the denominator of 2 separate terms?
I wouldn't even commit to something as strong as that. That would be true, but I would say that there would be more general situations. Maybe I can just pull up this tutorial just to give you just a quick reminder on to say what I'm talking about. So there'll be more general situations where n plus 1 and n, or k plus 1 and k both appear in the series, and then you need to rearrange it maybe with like partial fractions, or rationalize the numerator, rationalize the denominator, those kind of things. But the hint to know that you might want to do that is, yeah. So here was an example they gave you. So this was tutorial 6, is the one I keep referring to. Okay, and I think it was from K plus 1. Okay, so you look at this.
N and K.
Huh?
Is this N and K?
My apologies. There we go. So you might not know that this is telescoping, but your hint is, you know, one of the things you can do when you see roots is you can rationalize. Okay, rationalize the denominator, rationalize the numerator. And the hint is, because you see k plus 1 and you see k both appearing, there's a chance of it being telescoping. Okay.
So how would you calculate that?
How would you solve this? Well, I think the way we did this was we rationalized. So we said equals sum k equals 1 infinity of. So we multiplied by root k plus 1 minus root k plus 1 minus root k. Okay. So we just multiply by 1, and you get root k plus 1 minus root k. This denominator multiplies out to be just 1. Is that correct?
Yeah.
Okay. So, all right, and then you can say, okay, well, the partial sums, so Sn, the partial sum of something that's telescoping is always going to be the first term, only the first term and the last term in the telescoping survive. Okay, so the first term here is just going to be 1, and I guess the last term in a partial sum is going to be root n plus 1. I think this is right. Let me just check the solutions just to make sure. Not messing you around. Yeah, so.
The first term is 1.
So think about what's happening when you're plugging in all the possibilities here. Whenever you have telescoping, you have sort of a negative term, a positive term, a negative term, a positive term, a negative term, a positive term, and they all group in the middle so that one term on one end survives and one term on the other end survives. And you can say whether that's the first or the last. You can work that out. So I'm going to plug in k equals 1. I'm going to plug in k equals 2 and k equals 3 and k equals 4. The point is, this is the sort of what I think of as the first term. I'm not sure how else to say that. So if I had to write out what the series is, or let's just say what Sn is like this. What happens when I put in 1? I get minus root 1 plus root 2. Then what happens when I put in k equals 2? I get minus root 2 plus root 3. That's it. So the first term that survives is going to be there. And then it goes all the way up. I'm grouping this. Minus root 3 is going to appear, so on. And then there's going to be a last term where if I'm summing up to n, that last term is going to be root n plus 1. Okay? And since all of these terms in the middle are 0, we find out that the final partial sum is equal to root n plus 1 minus 1, okay? Which goes to infinity as n goes to infinity. Okay, so it turns out that in this particular problem, this diverges. Okay. But okay, so telescoping is something that is fair game to show up, but I wouldn't say that it's like central to the course, right? I'm just saying that this is something that has shown up in a number of times, a number of tutorial questions, a number of proofs that we've used for more abstract results. So I'd go back to kind of cut 6, question 1, to look at examples of telescoping. Okay, but the point is telescoping really does allow you to calculate what the partial sums are. And then once you know what the partial sum is, you can take the limit and find out what the infinite sum is, right? So we're looking for tools to calculate the partial sums, basically. Okay, and then what else did we have to do? So this was all kind of aside. Let's see if we have enough yellow chalk. Oh, there we go. So this little discussion over here was kind of aside, okay? And then what other tools do we have for calculating the partial sums? Well, one thing is you could check a few terms, guess a formula for Sn, and then prove with induction. Okay? So we did also do that in some of these workshops. So there are some recordings of that. Yeah?
So when you find your formula for S, and you still have to prove that it works for all of us.
Well, in general, yeah. So look, my advice to you would be like, if you write down the partial sums, it's going to depend on let me say it this way, it's going to depend on the wording of the question. So sometimes they'll word the question, they'll say, find a formula for the partial sums. And generally find means write down, perhaps motivated, but write down. If they say prove that the sum of this series is this or something, then prove it means prove, okay? Which means you got to prove every single thing that you did along the way, or point out that, oh, we proved that already in lectures or something like that. If there's ever any ambiguity, hand up in the test, hand up in the exam, right? I found this formula for the partial sums. Do I need to prove this with induction? Or do I need to prove this? And if they say yes, then how do you do that? This is your go-to tool almost always. Why? Because this depends on some integer n, or some natural number n. So proving these partial sums things with induction is often very quick. Sometimes we're used to induction, meaning like, no, not induction, it's going to take long. For these sums, it's usually very quick. Why? Because remember, your induction hypothesis is assume that whatever formula you found is true up to some n. Now you just need to prove it for n plus 1. But what is the sum up to n plus 1? It's just the sum up to n plus the next term. So very, very quickly, you can prove these things with induction. But check, before you spend time on it. Okay. And unless I'm forgetting something, I may have said something in one of the other workshops, but this is where I'd stop. This is what I'd say. So I'd say, like, if I'm asked to find the sum of a series, I really should just consider sort of these three things. First, quickly check, does it diverge? And second, is it a geometric series? Is it obviously telescoping? Even if it is telescoping and you can't figure out how to do it, you could do this. This would work. You could start writing out some of the sums. Yep.
Will we ever be given our influencing series?
We haven't really covered that in this course, right?
So it's safe to assume we'll not be given it.
Yeah, and the other thing is, like, we're always doing infinite series. So, can we have arithmetic series that are infinite? Not really, right? Unless I'm totally forgetting something. So the definition of an arithmetic series is like the difference between terms is constant instead of the ratio. But can you think of something that obeys that property that converges? Not really, right? Because if you're always adding a fixed number to every term, there's no way that that's going to converge as an infinite series.
Yeah, and you just said even if you don't know, even if you can't figure out like how it's telescoping, but you know that it's telescoping. You just said the telescoping series, even if you can't figure out how it's doing that, you can always do the third one.
Absolutely. Yeah.
So
this is always valid, right? If you can find out the formula and prove it with induction, you don't need to do any of these other arguments. I'm just saying these because these might also be useful. They might be faster.
So you're saying it's possible to see if a series is telescoping without knowing how the terms will cancel out?
That's not quite what I'm saying. So, maybe. That could also be true. What I'm just saying is, like, if you look at, let's say you looked at this problem, and you're like, oh man, remember Jonathan said if I see k plus 1 and I see k, that might be a hint that it's telescoping, but I just don't see it. I don't know how to rewrite this as something that's telescoping. Don't worry about it. Don't do it. Just do this. Just try write out a few terms, see if you can see the pattern. And actually we did this again in one of the workshops, so this is in the recording. We actually did it explicitly. We did question 1 with induction. So I would again say, see past workshop / try, this is messy, try cut 6, question 1. Okay, so try to do question 1A and question 1B on TUT 6, just using this method. Don't even worry about telescoping. Just see if you can write out a few terms, guess what the formula for the partial sums are, and then prove it with induction. And it is possible, and we did do it in the workshop. So if you get stuck, there's a recording somewhere, but it may be a little annoying to find exactly where we did it, but we did do it. So this is going to be like your bread and butter, I'd say. It's just that you don't only want to rely on this, because like, let's say you have a geometric series. Do you really want to spend time writing out partial sums if you can immediately see that it's a geometric series, or if you can rewrite it as a geometric series? No. It'd be much faster to just use one of these if you see them. The other thing is I don't want to leave you just with this, because this on its own maybe sounds intimidating, right? It's like, oh, write out the terms and guess the answer, and then prove it. What if you start writing out the terms and you feel like you can't see the answer? So you want other things to look at, maybe. Okay, so, and that's it. That's it for just, I need to calculate the sum. Yep.
Have they ever do, for instance, you know how we prove that, but the series, one of the harmonic series diverges, and we use the partial sums to prove that, but it is very specific, like there's an art to choosing which sums.
Yes, and I think, in that case, I think we still weren't, were we calculating the value of the partial sums, or we were still bounding it, right?
Yeah.
So that's still not going to help you in this case. It's coming in the next case. But yeah, but I get what you're saying. But it's not, that's not going to give you an exact answer, right? Yeah. It's just going to help you show something diverges. Yeah. I think in general that's a bit advanced.
Also, they're not going to ask us to do something like that.
I would say you might get a comprehension question on something like that. So you saw the one tutorial had a comprehension question on, I don't know if it was exactly that. I think it was more like on the divergence of p-series or something like that. But the point is they were showing you that you could group terms in a clever way and use the comparison test to do certain things. Yeah, that sounds like more a comprehension question type thing. Whereas I would expect more, you're gonna see things like these questions where it's like, here are 3 infinite series, tell me if they converge or diverge, and then you're gonna go, oh, should I use the ratio test or the comparison test or whatever? That's gonna be more what you're gonna do. It's more like the tutorials, right? In the tutorials, we didn't often say, please write out a long list of sums and then use a really clever comparison by grouping them in weird ways that you haven't really practiced before. We didn't really do that. The closest thing to that was just introducing you to telescoping. Okay, so let's move on unless there's any other questions on that. So all of that I'm thinking of as the style of question where it says, find the answer, find the number that this infinite series converges to if it does, otherwise tell me that it diverges. That's what you would do. So now, we have our other set of tools. For the more general question, which was saying series converges / diverges. Okay, absolutely. / conditionally. Okay, so just to say this all in words, I'm saying they just give you a question that says, hey, does this series converge or does it diverge? Does it converge absolutely or conditionally might also be part of that type of question. So now we're not finding the exact number that this infinite sum converges to. We're just asked to say, does it converge or does it diverge? Okay? And let's draw a little mind map so we're all like perfectly on the same page. So we start with a series. Whoops. And there are only 2 possibilities. Converges, does not converge. Okay? So if you're checking your series with one of the tools that we're going to discuss, and you get here, you're done. Okay, there's nothing more to say. But if you get here, you have 2 possibilities. Absolutely, or let's say absolute convergence, conditional convergence. Okay? That's it. Okay, so a lot of people were asking me in the tutorials or in other workshops, what do we mean by conditional convergence? Not absolute convergence. There are only two possibilities. Okay, so if it converges, there are only two possibilities, either this one or this one. So the definition of this one is that this one is false. Okay, and then just to be clear about what we mean about each of these steps, we're saying that the sum of an over here goes to equal some x. Okay, so literally this sum equals some number. Okay, here we're saying that the sum of an is not equal to x for all x. So there's just no number that this sum represents. Okay, this one we're saying the sum of absolute value of an equals to some x. And then this one, we're saying that the sum of absolute value of an is not equal to x. Okay? I'll just use my yellow down here, just to make sure that. Okay, let's just group that away. Okay. So this is very rough, but I think hopefully we're all on the same page here. So when I say this and this, then this is what we're talking about. So we add up our sequence, all infinite number of terms, and if it converges, but the absolute value of that sequence, of each of the terms in that sequence, adding that up, does not converge, we're over here. If the absolute value does converge, we're over here. And that's it. Okay? So there's nothing magical going on with conditional convergence. It just means that this is false. Okay? So now, what are the tools that we use to check this? Okay? So for two tools to check. Okay. So we always have geometric series. Okay, can check if it's a geometric series. Actually, let me just write it this way. To check diverging, same checks as in 1 for diverging. Okay, so we said you can check if the limit of AK is not equal to 0, then it diverges, the series diverges. You can check if it's a geometric series. And in principle, you could calculate the partial sums and see if they diverge or converge. Okay, so we're not going to rewrite all that, but I hope that that's kind of clear. We're trying to go through this quickly. Now, we've got this like list of tools, and I don't. So an greater than or equal to 0, or let's say k for all k. Then you can use the comparison test. Okay? Right? We cannot use the comparison test if we have negative terms in there. If all the terms are negative, that's fine too, because then that's the same thing as investigating the series minus 1 times that series. So just a minor comment there.
But can we take the absolute value and then use the comparison test?
Well, that's going to show you a mixture of conclusions, right? So if you take the absolute value, when you're investigating absolute convergence, that's always positive, so you can always use a comparison test. That's true. That's one part of your question. Another part of the question is, can I just do that up front? And, well, it'll work if the thing converges. But if you take the absolute value and it does not converge, you haven't finished the question. Why? Because from our mind map here, we're saying that there are situations where this series converges, but this one diverges. So if you investigate this one, you find it diverges, you still have to do more work. You're still going to have to go back and investigate that one without the absolute value. But if you take the absolute values and it converges, then you know that it converges absolutely and that the original thing converges. Okay? So if all the terms that you're working with are all positive, and maybe I should say, or AK less than or equal to 0 for all k. So if they're all positive or they're all negative, you can use the comparison test. Okay? If they're alternating, which one are we going to use? We haven't really, we're going to use alternating series tests. And we haven't really covered anything else. Okay, there are other tests that will be useful there, but we haven't done that. So if alternating, so in the same here, you see something like -1 to the k plus 1. If you see that somewhere, it's probably alternating. Then use the alternating series test. I'm not going to write that all out, but alternating series test is what I mean by that. Okay. And then what do we have left? As far as I recall, we have 2 left that we've covered. I don't think we've covered much more than that. Ratio and root text.
Oh, just very
Yeah, I'll think of P series as being kind of grouped in here. There's actually a lot. This is like, it's very easy to just use the comparison test, but there's actually a lot of theory built in there. But yes, so we'll think of that as just being in the comparison test. So then we're going to say over here, if you see k factorial, kind of k to the k, a to the k, etc., ratio test. Okay?
Even k to the k.
Yeah, it turns out it might not be, but what I mean is these are sort of roughly, so like rough. So I might say something there like, what if you had k to the k over k factorial?
Oh.
Okay, so we saw that one before, right? And it's like the k to the k makes you want to use the root test. The k factorial makes you want to use the ratio test. Guess which one's going to be better overall? The root test is generally our last go-to because certain things, taking the kth root of them is a pain. Working out the limit. It's not impossible. It just requires more work. So.
Do we need to know the integral test?
The integral test.
Yes.
If you know it, it's useful sometimes. For example, proving the divergence of the harmonic series is extremely easy with the integral test. But we haven't covered it, so it's sort of up to you. As far as I understand, we haven't covered the integral test, right?
Integral.
Yeah, there's something called the integral test where you literally do an integral. Yeah. So once you see it, you'd say, oh, why didn't we cover that? Because it's not that hard to explain. It's probably more intuitive than, say, the root test. The root test doesn't have a nice picture associated with it. The integral test is quite straightforward. But anyway, we haven't covered it. I'm not sure if we will cover it. But if you know it, you can use it, I think. I mean, again, double check with the lecturer. So, okay, and then if you see we had an example like this in the tutorial, but like a to the k squared, stuff like that, k to the k, 4 or something. You start seeing these weird powers of k around, then root test. Okay, and I'm really not going to be able to exhaustively kind of show all the different ways, but I hope that we get a feel for the idea that kind of k factorial is always naturally going to go well, or anything factorial is going to go pretty well for the ratio test. Certain exponents are pretty great for the ratio test, but something like this will be a pain, perhaps, in the ratio test. Maybe not. Whereas the root test would be very easy here because you just put 1 over k, right? That's what taking the kth root does. And I just want to remind you all that of this technique of saying that when you have like x, and let's say you wanted to calculate the limit as n goes to infinity, okay? This is equal to the limit as n goes to infinity of e to the ln, is it 1 over n ln x? Is that what I want to say? Yeah.
Okay.
Yeah. And then this is equal to the limit, to e to the limit as n goes to infinity of 1 over n ln x. Okay? You may not be familiar with that technique, but that is true. If you want to know the abstract reason for why this works, well, these are just equal, right? This guy is actually equal to this because we know that e to the ln x is just x. And then I just am multiplying the whole thing. Multiplying the two exponents together is the same thing as raising this guy to that exponent. No, are we all happy with this? I'm not making any mistakes. Sorry, I had a sudden moment where I was like, and then the point is, this is a continuous function. So we'll actually see it later in the course, but you may have seen these techniques in Man 1000, I'm not sure. But you can pass limits through continuous functions. And if you wanted to, you could actually draw a picture of saying, like, what if I had some function in here? And okay, there are certain conditions on whether the function in here is behaving well. But anyway, the point is, for this type of problem, this is true.
So can't you continue from there? So as if we can continue, because we know the limit is n.
Well, I haven't said what x is. So I'm giving you a broad technique. So what if x is like n factorial divided by e to the n, or something? Like I haven't said anything yet. I know you're thinking maybe x is just literally the variable x, or it's like a number. Then yes, we could say quite quickly what's going on. But what I really mean by this is I should have probably put like a function of n. So if you wanted to change your notes and say, well, I have some like f of n, then I would have an f of n there and an f of n there. But I thought that might obscure more. But anyway, so this is a technique. I don't know how often you'll encounter this. You may even encounter this less than telescoping, for example. I don't know, but I just want you to be aware of this. This is something that like you got to see it once. If you don't see it, it's pretty hard to figure out that you can do this. And it does resolve certain types of questions where you need to do the root test. Okay? But hopefully we'll get to some examples like that. And then, let me just scroll this up. And then, I would just say like there's some other things, sort of broad other list of things that like are much less the bread and butter of what we're doing. So there's stuff like monotone convergence, Cauchy sequences, etc. Okay, so you can use these sorts of tools in the situations of answering whether a series converge. But I don't think it's going to be worth our time just discussing every single possibility of what can happen here. Maybe it's something for Murray tomorrow. But I think we should get into some examples now. It's pretty much, unless there are any more questions about this sort of overview. But yeah, the key idea is just like, when do I use the comparison test? That's going to be helpful with like certain functions that you know well. And honestly, a lot of the time, the ratio test and the root test are just going to be faster. But don't not practice the comparison test, or said another way, also practice the comparison test.
Related to question 2, here we have a k factorial
A and H.
over k to the k, right? Yeah, so
Well, we're going to do that question right now. So
yeah, I want to ask.
Oh yeah.
So sometimes it helps when you're keeping a ratio to figure out which grows faster to help you.
Yes. Oh, okay.
Right? So which grows faster, k factorial k to the k, constant to k?
So we actually learned from that question that k to the k and k factorial are sort of growing about the same. Because that limit exists. Okay, I think that's a fair conclusion. But what we definitely know is that a constant to the k is growing slower than k factorial. I think we actually proved that last time, because we showed that we could compare with the geometric series.
And is K2 constant grow less than A2?
Then k factorial and less than a to the k, yes. So the hierarchy actually, just to write this out really quickly. So the hierarchy I would kind of think of is something like this, like ln k is always going to be less than polynomials in k. In other words, your question k to the a, okay? It's going to be less than kind of 2 to the k, a to the k, e to the k, all these kind of exponential or power functions. And then that's going to be less than kind of k factorials. And then that, I think we're learning that these are about the same as k to the k, but this part I'm a little unsure of. I should probably know the answer to that as your tutor, I'm sorry. But you'll see in the question that when we calculate the sum, it really does converge.
But I think K to the K grows faster. It's K to the K, it's K times K.
Yeah, I would have thought that it was like this, but then I'm a little bit thrown by the fact that the sum converges, right? That makes me feel like it's not true that this one is growing substantially faster than that one.
No, but doesn't that go to E? Because the inverse goes to 1 over E.
Exactly. So because this one converges, it makes me feel like this numerator can't be growing much significantly faster than the denominator. Do you get what I'm saying? But probably when we're getting into this realm, I need to adopt like particular conventions of what I mean by growing faster. But do we agree that sort of in this picture the whole idea was like I said, say k over ln k, that series is going to diverge, okay? Just because the numerator is just getting so much bigger than ln k, okay? What I mean by that. We agreed that this is going to diverge, okay? Whereas this one does not diverge, okay? So that's sort of interesting to study. How do these two interact as k gets large? Certainly, this one has to grow bigger than this one enough to make this overall limit 0. So possibly what you're learning there is even that. Well, I guess we can already say actually that this is true. But actually, I don't think we are even confident about that.
Actually, k factorial over k to the k.
Yeah, but both converge. Okay, so for example, if I have ln k over k cubed, this is going to converge. Okay, and really the sort of the intuition there is something like k cubed is going to grow a lot bigger than ln k, and in fact, really the particular balance that we need is that ln k is less than k, and that's going to give us sum of 1 over k squared. Whereas in this case, both this one and its inverse converge. So there's a really special balance between these types of functions that I don't know enough to tell you exactly at this moment. So sorry about that. If I learn a bit more, I'll tell you more. But all I would say is for the purpose of answering questions here, don't worry too much about the growth rate between these two, except you need to know that this does converge and how to show it, and it's going to be the ratio test. You could also show it with the root test probably. But okay, let's go into that example and see that. Whereas like you saw that, so that's a delicate balance where I guess my point I'm trying to make to you, I'm not sure if it was clear, is this one will converge, but obviously this one diverges. Okay? But in this case, you actually have a really special relationship where this one converges and its inverse converges. Okay? Yeah, and that's quite wild. But okay.
Are we doing tab 9 now, right? Are we doing tab 9?
Yes, so we're going to do TUT 9, and I think we'll start with, we'll just try to do A and H quickly, and then we'll see if we can get through question 1. All right, so I think a few of you asked me about question 1 in the tutorial, like actually on the day of the tutorial, so hopefully it won't be too fast if I just say, as I said in that guide, so this is sorry, not question 1, this is 2A, and we're asked to calculate k equals 1 and k factorial over k to the k. And as I said, you see factorials, you see exponents, this is going to be a natural place to do the root test. So we're going to check a to the k.
You see ratio.
Sorry, ratio test. I said the wrong word, but I wrote what I want to do. So we're going to calculate this, the limit as k goes to infinity. All right, and we know that we're going to get the limit as k goes to infinity of k plus 1 factorial over k factorial, and then we're going to have k plus 1 to the k plus 1 over k to the k. All right? And we want to get quick at writing down these ratios. So you just write down the first one with k plus 1 substituted in, and then you just invert this without even thinking about it. So that's what you see here. All right, so what is this equal to? Limit k goes to infinity. All of the terms in this cancel except for the k plus 1 term. I have a k plus 1 to the power 1 from there. Okay, and then over here, I just have k over k plus 1 to the k. Okay, so I had a factor of k plus 1 that I pulled out over here. This thing, all of the terms in it cancel except for the k plus 1 term, because it's the product of k plus 1 down to 1. This is the product of k down to 1, so everything cancels except for that k plus 1. And then I just have k to the k over k plus 1 to the k. So I write those all to the power of k. This cancels. So I have equals limit k like this, k over k plus 1 to the k. And as I said to a few people in the tutorials, this is a kind of an interesting limit because in general, when you're raising something to a power k, you might think that if the thing inside is less than 1, raising it to the power k will make it smaller and smaller and smaller. And if the thing inside is greater than 1, raising it to the power k will make it bigger and bigger and bigger. But in this case, the thing inside is not a constant. It's not a fixed number. It's actually depends on k as well. So raising it to the power, this is less than 1, but raising it to the power k might be making it smaller and smaller, but at the same time, this thing is getting closer to 1. So there's sort of two opposing forces. This thing wants to get closer to 1, so bigger as k gets larger, and this makes it want to get smaller. So we don't actually have a good intuition for what this does, except for the fact that we should recall that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. Okay? And this is exactly the same situation where you have something inside that depends on n but also being raised to the power n. Written this way, you can see that as n goes to infinity, this thing inside wants to get smaller, but the power n wants to make it bigger. Okay? And if we simplify this, this is equal to the limit as n goes to infinity of n plus 1 over n to the power n. Okay? And we make the observation that maybe some of us saw in the tutorial that this is just the inverse of that with, okay, this I used n, there I used k. So the point is, we need to know this limit. We have to have this memorized, possibly even Google a proof for it if you want. And we know that this is the inverse of this. And we have from our basic limit laws that the inverse of a limit is the limit of the inverse if the limit exists. So this just equals 1 over e. Okay? And what did we need to check? We needed to check if this was less than 1. 1 over e is definitely less than 1. Okay? Because e is something like 2.7, right? Or something like that. So we learned altogether altogether, series converges. And I think we can say absolutely, yeah? Because the ratio test does that for us. Okay, in this question, they didn't ask you to say that it converges absolutely, but just making that comment that the ratio test really does tell you.
The ratio test tells us that the thing does converge absolutely.
Yes.
In class, we had absolute values.
Right, but this is all positive, right? So,
Okay, so in this special case, we don't have to put absolute values.
yeah, I mean, you're only going to put the absolute values if the thing's positive, negative, has negative terms. So I could put this if you want.
So whenever we're using the ratio test, you always put absolute values, except if the thing's always positive.
That's true, but that's actually the opposite of the way I think of it. So, but it doesn't matter. They're all the same. So the way I think of it is I can use the ratio test always, and if I see negative numbers, put absolute values. But yeah, it's the same. Yeah. But you're still just applying that formula, right? Yeah. All right. So then we were asked to do H. Okay, and then in H, well, I want to do G before we do H, because there's a comment I was going to make on A, but let's just make it on G. So in 2G, we were asked to check this sum. K equals 1, K over K plus 1 to the K factorial, or K squared, sorry. Now, again, this looks a lot like our sum of 1 over e, or a limit of 1 over e, or something like that going on. But we see that, you know, if we wanted to do the comparison test, this could get messy. If we wanted to, we could perhaps do it. If we wanted to do the ratio test, this part is going to be easy for the ratio test, but this part might get a bit messy, okay? Just because we have that. If we just had a single power of k, it would be fine, but like k squared, we could still do it. You're going to end up getting some polynomial in k when you put it in k. If you're going to put k plus 1 squared here, and you're going to divide by something where you just have k squared, you could still try to work it out. But this is really going to be a natural place for the root test. Okay? Why? Because we have something raised to like the power k, and especially to higher powers of k. Okay? So when we do so let's just check. As we said in the guide earlier, that this is, when we see this is going to be a natural time for the root test. Okay, so we need to check this 1 over k of k over k plus 1, all raised to the k squared. Okay.
I don't know if I like your convention. You said 1 over k, the root of 1 over k. Shouldn't it be?
Should I just write k? Is that that's probably what's confusing me. Because when I was doing the thing earlier, so please go back and fix your notes. I was looking at it and I was like, there's something not right here, but I just don't see it. I don't know if I'm tired. Thank you. This is correct. Sorry. And we know that this is just, so earlier on when I showed the exponentials and stuff, I made a mistake in the notation. Sorry. So we know that this is literally just equal to k over k plus 1, k squared over k. So that kth root just makes us divide by k here. And now we really see why the root test is powerful for this type of question, where we have higher powers of k. Okay? And so that's just going to equal to the limit k goes to infinity of k over k plus 1 to the power k. We cancel the power of k. And we've seen what this limit was. Okay, this is equal to 1 over e. Okay, we just did that in the last question. Yeah.
I'm thinking if maybe we had a k to the 3, right, or something like that, would we have to use the root test twice?
Would we have to use the root test twice? I don't know if you can use the root test twice. Somebody asked me this in the tutorial as well, and I forgot to look up on it. They asked me, can I combine the root test and the ratio test in some way? And I was like, I don't think so. I think what you'd do in that scenario, well, you want to know how to calculate this limit, right? Okay. And my guess is perhaps that's going to diverge, but I don't know. I don't know, maybe that will, because you might be in a situation where, well, there, I mean, at the end of the day, you could try to like do L'Hopital's rule or something, right? Because at the end of the day, your question is like, can I calculate that limit if I have a k squared? Okay, so this limit's easy to calculate just because we know the answer. If you're in a situation where the limit that you find is more complicated, maybe you have to do L'Hopital's rule.
If that's the case, then with that, we can also do L'Hopital there as well.
Where?
There.
Here?
There.
But remember, here we're not just trying to calculate the limit, right?
Okay.
Right, because we're trying to calculate the limit of the partial sums. We could check the limit in here to check if it diverges. But we can't tell if it converges by taking the limit, if the limit exists. So yes and no, right? Whereas what this test does is it says calculate this limit, and if it's less than 1, then we know the answer of summing this, which is actually quite a wild thing. That's quite different from saying just calculate a certain limit. Summing this is quite a different thing, right? Because we're summing up the partial sums and then taking that limit of the partial sums. But okay, so we know the answer to this, okay? So now we do H, which was a very similar series, but we just had a 4 to the k. Okay? And we're again going to use the root test, because we saw this and we thought, well, that helps. The root test is quite nice here. And do I have any problems here? No. Taking a kth root of this is also going to be nice. So I still feel like using the root test. So, and I just need to calculate the kth root of this, which I know, I've already worked out the limit of everything. So I know, without doing any more work, that all I have to calculate is 1 over e times the limit as k goes to infinity of the kth root of 4 to the k.
Excuse me. That limit, it's equal to a constant. It only tells us that the sum converges. It doesn't tell us that the sum is equal to that.
Exactly. It only tells us that so we're just saying here, less than 1. Okay. Similar with the comparison test, right? In the comparison test, you might bound it by a constant even, or bound it by something. Okay, not by a constant, but you would bound it by something, but that's not going to tell you whether what the number is. That's why we broke the things up into two categories, right? So we have type 1 type of question, find the sum of a series. Type 2 type of question, does the sum exist or not? Okay, does the sum exist or not is a different question from find the sum, because just different tools will apply, right? Here we're able to say whether the sum exists. The sum does exist, okay? We don't know the result though. That would be, we'd need to use some other tool. The root test will not do that for us, okay? All right, so in this case, we're again using the root test. I need to calculate the kth root of this whole thing and then take the limit as k goes to infinity. But I know that if the limits exist, the product of the limit is the limit of the product. So I've already calculated the limit of the kth root of this part. So I just put that here. I don't do that work again, okay? Don't do that work again if you're in the test or whatever. It'll take way too long. All I have to do is now work out the kth root of this factor, okay? And that's just going to equal, it's just a constant, because the kth root of this is just 4. So this equals to 4 over e, which is greater than 1. So it does not converge. You all happy? We got to know also, I mean, I think all of you know that E is about 2.7, so don't spend time on the calculator. That's a waste of time. Yeah. So it does not converge. Oh, you're not allowed calculators anyway. That's probably why. Okay, so any questions there?
I just wanted to ask, just about the comparison, checking if it's greater than 1. Is it Did we learn what to do if it's inconclusive, if it's equal to 1?
I don't know if you've discussed that in the
They
class.
say that if it's inconclusive, then basically you've used the wrong test. Try
Oh.
another.
Yeah.
It's not telling you anything about anything.
So, yeah, it would be interesting to see if they give you something where the limit's 1. That's a fairly good question, because they haven't...
And one of the n squared, because one converges and the other one diverges. That's the example they use in class. When you check the...
What were you doing there? The ratio
the
test?
I think it was ratio.
Okay.
Yeah. And if they both went to 1, then one converges and diverges.
I see. Yeah, that's kind of interesting. Yeah, I could also imagine cases where taking the kth root produces things that maybe the limit just doesn't exist or something because it's a weird... but yeah.
Sorry, so with this example, what if it was 4k squared and then you ended up with 1 over e multiplied?
So you're saying you want to do this one?
Yeah.
Like that?
And then you ended up with the limit of 4 to the k, but then 4
That
is
it just...
greater than
Oh, I see. And then you're... so that's a very good question.
It's like it's not, the limit does not exist. So can you still use the fact that it diverges and then saying it's greater than 1 and then...
So I think the statement of the theorem that they've given you is that if the limit does not exist, it's inconclusive,
Oh, okay.
right? Can anyone check that for me? As far as I recall, that's what it says. Or I can Google it quickly. I don't want to. That's what I recall. I don't want to tell you the wrong thing and then have you memorize that. But as far as I understand, if the limit is 1 or the limit does not exist, it's inconclusive.
Yeah, both of them are just talking about if the limit exists, then if it's greater than 1, less than 1.
Let me get on the Wi-Fi here and just make sure that I give you the right answer.
Yeah, because the limit now is the No, but then that means we just use the wrong test, because obviously we can't use it to say the limit is greater than 1, it's less than 1. Yeah.
Oh dear. Doesn't want to let me on the Wi-Fi.
Because I realized when I just told you that it doesn't necessarily mean greater than 1. So this will be 10 seconds. It's a bit funny. So I want to, man. So I have some ideas of what I want to say to you, but I'm a little bit wary of just giving you like weird. So in the ratio test, I have a Wikipedia article that just tells you straight that if the limit equals 1 or the limit fails to exist, then the test is inconclusive because there are convergent and divergent series to satisfy this. And then they go on to a more advanced discussion, which we haven't covered in this course, of how you could sort of like make the test apply to a few more cases. But so for the ratio test, they explicitly say on Wikipedia that if the limit fails to exist, the test is inconclusive. Now, for the root test, it's a bit funny because they define the root in terms of lim sub, which isn't the way that we did it. So I wonder if I could, on the spot, tell you. But what I would say to answer your question in this particular case, you know what to do, right? Is if you had k squared here,
So now we're doing a different problem, not to confuse anyone. You had k squared there, then you have k squared here, and then you found out that this equals, this goes to infinity. You might be in comparison test land or something like that. Okay? Because, well, cheating a little bit because we already did the other problem, you know this. You see, and then we can use the root test on that. Okay? Now, okay, I already knew the answer to that when I did this, so is this the most clear? So, you know what, take that to Murray. That's the reason he's the lecturer and I'm still a tutor. But I feel like